chemical reactions. So we're kind of starting off another slightly different topic here. So chemical reactions involve chemical changes. We have one substance being destroyed, one or more substances being destroyed, and one or more new substances being formed. And chemists are very interested in chemical reactions. It's important to understand that this is like building with Lego blocks, where you take the pieces apart and you put them together in new combinations, but no Lego blocks are harmed in the process. Atoms are not created or destroyed in chemical reactions. We use chemical equations as a shorthand to describe chemical reactions, because if we wrote them out in words, it would be very tedious. It'd be tedious for the person writing it down. It'd be tedious for the people reading it. And so we have come up with a concise method of writing equations to communicate what's going on. The general idea is that the reactants react to produce the products. Okay, so we've got reactants on the left, the arrow points to the right, and those are the products that we end up with. So just like we read and write from left to right, the reaction seems to go from left to right. Reactants are on the left, products on the right. There's a lot of information in these equations. We're going to have the formulas of the individual compounds and elements. Oftentimes, we're also going to have their states. Is it a solid, a liquid, a gas? Is it aqueous, dissolved in water? A lot of times that's included as well. We are going to have the relative numbers of reactant and product molecules. If you have hydrogen and oxygen reacting to form water, well, the formulas tell us that it's molecules of hydrogen and oxygen, and the formula is also, the equation is going to tell us that it's 2 moles of hydrogen for 1 mole of oxygen. We can use chemical equations to figure out the mass of product that will be produced or the mass of reactants that we need if we want to produce a certain amount of product. So very, very practical and lots of information. These are the state symbols. G for gas, L for liquid, S for solid. Those aren't hard to remember. AQ is for aqueous. Aqueous means dissolved in water. It's a little like the Spanish word agua, so if that helps. So that just means in water. Yes?
Can we use the little wave sign instead of aqueous?
No, you have to use AQ, because that's what chemists do. So let's look at the combustion of methane. Methane is the primary compound in natural gas. And when it burns, it produces carbon dioxide gas and water in the gas state. The water's in the gas state because when methane burns, it's hot, right? And when water gets hot, it evaporates. Important to remember that whenever something burns, it combines with oxygen gas. If there's no oxygen present, it will not burn. So here's our equation. CH4, that's the formula for methane, and G, telling us that's in the gas state. That's going to react with oxygen. Oxygen is one of those 7 diatomic elements. That's why we write O2. That's in the gas state. And this is forming carbon dioxide, gas, and water gas. So there we have a very simple chemical equation. But there's a problem. If these were Lego blocks and we had 1 carbon, maybe 1 black one and 4 white ones and 2 red ones here, we could not combine these in a way that we would have 1 black one, 2 red ones, another red one, and 2 white ones here. On this left side, there are 2 oxygen atoms. On the right side of the equation, there are 3 oxygen atoms. Can an oxygen atom be created in a chemical equation? Chemical reaction? No, it can't. So there's something wrong with our equation. It's not complete. The other problem is with the hydrogens. On the left side of the arrow, we have 4 hydrogen atoms, and on the right side, there's only 2. Did 2 hydrogen atoms disappear? No. Did 2 hydrogen atoms turn into 1 oxygen atom? No, that's a creative solution to the problem, but that doesn't happen. Red Lego blocks do not turn into green Lego blocks when you're building. And hydrogen doesn't turn into oxygen. So this equation is violating the law of conservation of mass. Because if we added up the mass of all these pieces and the mass of all those pieces, it's not going to be the same. So we fix this by what's called balancing the equation. The numbers of molecules that are combining is not 1 to 1. When we balance an equation, we add coefficients. A coefficient is a large number in front of the symbol. I'm sorry, that's something else. This 2. 2 in front of the formula for oxygen means that there are 2 of those. We can't change the subscript. We can't say, oh, well, if I make it O4, it's balanced. Well, it would be balanced, but O4 doesn't exist. It's O2. We've got 2 O2s. And then we put a 2 over here, and that solves our problem with the hydrogens. And so here we have it in pictures. So we've got 1 methane molecule. There's 1 black one here and 4 white ones. We've got 2 oxygen molecules, so 4 red balls. And you can imagine taking those apart and putting them back together and forming this combination over here. 1 black one still. Here's 2 of the red ones, and there's the other 2 red ones. There's 2 white ones and the other 2 white ones. That's a balanced chemical equation. When you understand what the symbols are meaning, balancing equations is much easier. I can teach you steps to go through and balance them, but if you can't picture them as balls or Legos being taken apart and put back together, it's a lot harder. Does anybody have any questions? So how do we balance chemical equations? These are suggested steps. First, you need a skeleton equation, just the bare bones. So that has formulas for the reactants and products. It's really important that the formulas are correct. Earlier in chapter 3 here, we've learned how to write formulas. And there will be questions where they give you names of compounds in the reaction, and then you have to write the formulas from the names. They really, really need to be correct. Next, we're going to balance the atoms that occur in more complex substances first, and we're always going to do the compounds before just the pure elements. This is a suggestion. This technique is called balancing by inspection, meaning you look at it and you balance it. These are guidelines that we know make it easier sometimes, most of the time, but doesn't mean that you have to do it that way. Leave the atoms that occur as free elements, like oxygen or hydrogen or something, for last. The reason is that when you fix those, they don't mess anything else up. You can end up with coefficient fractions. You can also avoid having fractions, but sometimes you'll end up with fractions, and what you do is you multiply all of the coefficients by the denominator of the fraction, and that'll get you whole numbers. The last step is really important. Go back and check through it again and make sure that you didn't miss something. Let's do an example. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. We need formulas. And we need to identify what are the reactants and what are the products. So there's clue words in here. To produce. That's the arrow. Everything before that was the reactants. To produce, the things named after are the products. Okay, silicon dioxide. Is that an acid, an ionic compound, or a molecular compound? It's molecular. So how do we know that? Well, find silicon on the periodic table. Which side of the stair-step line is it? It's on the right side with the nonmetals. I've never seen this in print, but what I've observed with those semi-metals, and silicon is a semi-metal, what I've observed is that the semi-metals that are on the non-metal side get named as non-metals. And the semi-metals on the metal side get named as metals. So silicon's on the side with the non-metals. This is two non-metals then essentially, silicon and oxygen. So the prefix di tells us how many. So what we're going to do is we're going to write Si for silicon. There's just one. And dioxide means two oxygens. What's the state that this is in? It's a solid. So put S behind it. Plus, I'm going to leave a space because I might need to write a coefficient in there. Solid carbon. So C, and it's a solid, but then this is an element. You have to ask yourself, is it one of the 7? No. Chlorine is, but carbon is not. So it's just C. And then I have that to produce solid silicon carbide. What kind of a compound would that be? Molecular. So Si, C. There aren't any prefixes in that one, right? So occasionally they drop the mono on the second one too. So if you come across one like this where the mono is missing, our rules tell us it should be silicon monocarbide. There's reasons why people sometimes leave the mono off. And that's a solid. Plus, carbon monoxide gas, CO. So CO, and that's a gas. Any questions? Really important to learn the nomenclature, because that's going to mess things up if you don't know that yet. So we've got our skeleton equation. Now we need to balance this. I'm going to show you 2 methods. So the first is really more of an eyeball, just kind of looking at it thing. Here I've got carbon all by itself, and so I probably want to leave that one to the end. I have found that a lot of times you can just kind of go left to right, and it'll work out. And here's another tip. If you start balancing it and you find that you're going in circles or it's really not working out, you're like, this is impossible. Check your formulas, because if the formula's wrong, it could be impossible to balance. And then start over with a different element. So I'm going to start with silicon. I have one silicon on this side of the arrow, and I have one silicon on that side of the arrow. Cool, that works. Then I'm going to look at oxygen. How many oxygens here? 2. There's none in this guy. Over here, no oxygens. Here I have 1 oxygen. How can I get there to be 2 oxygens on the right side? I put a coefficient 2 in front of CO. I can't make it into carbon dioxide, but I can, well, there must be 2 carbon monoxide molecules. Now I've got 2 oxygens on both sides. Next, I'm going to look at carbon. Here I have 1 carbon. And how many carbons on this side? 3. There's 1 here, and there's 2 there. Because carbon is by himself, when I put a 3 in front, that's not going to mess anything else up. Any questions? So here's another way to do it, which some students like. Draw a line at the arrow and think about like balancing like a teeter-totter. I need everything on the left to be the same as on the right. And then I'm just going to make a little list. This method seems a little silly on a simple equation like this, but when things get a little more complicated, it might be more useful. I'm just going to list the elements in order that I run into them: silicon, oxygen, and carbon. And then I'm just going to take inventory of what I've got. So here I've got 1 silicon and 2 oxygens. Over here, none and none, but I have 1 carbon. I said no carbons in that guy. And then I'm going to go to the other side. Here I have 1 silicon and 0 oxygens and 1 carbon. Here I have no silicon, 1 carbon and, 1 oxygen and 1 carbon. You with me? I took inventory. Now, for this first row, for silicon, I'm going to compare the total of the left side to the total of the right side. It's the same. Awesome. Then I'm going to look at oxygen. On the left side, I have 2, and on the right side, I only have 1. To fix that, I need to multiply this by 2. So I have to put a 2 up here, and then that changes everything underneath. So you have to adjust your inventory. Now I've got 2 oxygens on the left, 2 oxygens on the right. Next, I'm going to look at carbon. Total here, 0 plus 1, 1 carbon. Over here, 1 plus 2, 3 carbons. Well, if I multiply this by 3, then I get 3. And that doesn't change these guys because there weren't any silicons or oxygens there. So different approach, same result. Any questions? Let's do another example. Write a balanced equation for the combustion of gaseous ethane, C2H6, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. So here is the to form. That's our arrow. We've got ethane combining with oxygen. Those are the reactants, forming carbon dioxide and water. We need the formulas. So they gave us ethane, C2H6. They're telling us it's a gas, so I'm going to write G for the state symbol. Combines with oxygen. Is oxygen a diatomic element? Yes, it is. We have to write O2 because this represents substances as they are, not as we would like them to be. To form carbon dioxide. We had carbon monoxide in the last one. Carbon dioxide is CO2. Again, it's a gas. And water. Hopefully we've used water as an example enough that you have that one memorized. H2O in the gas state. Questions? I'm going to do the tally method. So I'm going to draw a line down the middle, so I'm real clear on left and right. I'm going to make a list of the different elements I've got, carbon, hydrogen, and oxygen. In this first compound, I've got 2 carbons and 6 hydrogens. No oxygens. In the second substance here, no carbons, no hydrogens, 2 oxygen atoms. Over here, 1 carbon, no hydrogens, 2 oxygen atoms. And in the water, no carbon, 2 hydrogens, 1 oxygen. Everybody okay with that? So I'm going to start at the top. Here's carbon. I have a total of 2 on the left and only 1 on the right. How do I fix it? What if I put a 2 in front of the CO2? That's going to multiply all the numbers below. So now I've got 2 carbons and 2 carbons. Carbons balanced. Next, I'm going to look at hydrogen. Here I've got 6 plus 0, total of 6 on that side, 0 plus 2, only 2 on the right side. What do I multiply 2 by to get 6? 3. So I'm going to put a 3 in front of water. That'll multiply everything underneath. So this is now 6 hydrogens and 3 oxygens. So the hydrogen's balanced. Now I'm going to look at the oxygen. 2 on the left. Total of 4 plus 3 is 7 on the right. What do I multiply 2 by to get 7? We could get into fractions, but as my friend who teaches junior high math says, fraction is the F word to a lot of students, and people don't like fractions. So how do we get around that? So here we have an odd number, and these are coming in pairs. I call this the odd-even problem. It shows up a lot in these combustion equations. How do you change an odd number into an even number? Multiply by 2. If we doubled everything, the odd-even problem is going to go away. So I'm going to double this, and I'm leaving the oxygen alone because that's the one I'm messing around with right now. I'm going to change this 2 into a 4, and I'm going to change the 3 into a 6. Okay with this? Now I have to adjust things below. So now I have 12 hydrogens and 6 oxygens, right? Over here I've got 4 carbons and 8 oxygens. And don't be alarmed that these numbers are getting a little bit big. It's okay. Now I've got 4 here and 12. So we messed around with things. Let's double check carbon. 4 plus 0. 4 plus 0. Carbon's still okay. Hydrogen. 12 plus 0. 0 plus 12. Hydrogen's still okay. Now for oxygen, we've got 8 plus 6. We've got a total of 14 over here. On the left, we still have the 2. Oh, that's easy. Multiply by 7. We multiply this by 7. It changes the number of oxygens, but doesn't mess with the carbon and the hydrogen. And there we have our balanced chemical equation. You should always double check at the end. Here I've got 2 times 2, 2 carbons. I'm sorry, 2 times 2 is 4. 4 times 1, 4 carbons. And you just go through and you check everything like that. Any questions?